Hi dear students, a very good morning to you all. So let's start with the next topic from electrical potential energy and capacitance. Electrical potential and capacitance. So today's topic is electrical potential energy. So write on the first heading, electrical potential energy. Electrical potential energy. Okay, I'll define couple of points, then we will start to analyze what it is. Okay, first point, electrical potential energy. Electrical potential energy for a charge, which means for a charge, which means for a single charge, it is equal to 0. Next one, electrical potential energy exists for a system of charges, which means that what we can find electrical potential energy for a system of charges, which means we have more than one charger should be there, then we can say electrical potential energy is exist. But for a single charge, electrical potential energy is equal to 0. I will take an example so that it will be much clear to you. So we'll take a triangle structure. Okay, so this is maybe side A, and this is B, and this is C given. So the charge which is placed here Q1, charge which is placed here Q2, charge which is placed here Q3. Now, if you are asking me what is the potential energy of the charge system, this is an equilateral triangle with a side length is equal to A. So, we are calculating the potential energy. So, potential energy for a system. System means it should contains more than one charges. So, more than one charges means minimum combination is how much? 2 charges, right? So, Q1, Q2 will form a potential energy. So, total potential energy is equal to potential energy due to charge 1 and 2. And potential energy between charge 1 and 2 is over, and 1 and 3. Any other system? Yes, potential energy between 2 and 3, potential energy between 2 and 3. Anything else? Nothing. All the combinations we have taken, 1 and 2 is taken, 1 and 3 is taken, 2 and 3 is taken. So if you are adding the potential energy due to two charge systems all together, and finally we got a single potential energy. Okay, so we are calculating the potential energy of the system U12 plus U13 plus U23. So all together we'll get a total potential energy of the system. So we'll first find the potential energy due to 1 and 2. Okay, so what is 1 and 2? K into potential energy is equal to K into the product of the two charges Q1, Q2 divided by distance between them. This is called potential energy. So K into Q1, Q2 divided by A plus second charge 1 and 3. 1 and 3. So K into Q1, Q3 divided by A plus between 2 and 3. So K into Q2, Q3 divided by A. This is the total potential energy of the system of charges which are on all the sides of the triangle. So, electrical potential energy is applicable for a system of charges, which means two charges are necessary, then only electrical potential energies are exist. So, electrical potential energies always exist for a system of charges, which means more than one charges, minimum 2 charges is required, then the total potential energy can be found out. So, in very short, you have to remember only these equations. U equal to, wherever you are asking potential energy, K into two charges Q1, Q2 divided by distance between them. So if you remember this formula, we can use it in many places and be able to find out the answer for the question also. So potential energy is equal to K into Q1, Q2 divided by R for a two system of charges. So if you have like a 3 system like this, so between every 2 charges potential energies are exist, and we need to calculate the total potential energy by taking the 2 charges each of this one. So this is a concept behind this one, potential energy. We'll move to the next topic. So next topic is related with what we have learned before, which is called electric dipole. Okay, Hope you already remember what is called dipole and what is called dipole moment and what is called a stable equilibrium and what is called unstable equilibrium. And if you have to remember all these things, if you have not remembering, so pause the video and kindly have a look into your notebook where you have learned about electric dipole, then come back to here so that it will be easy for you. Okay, so we will write electrical potential energy, the next heading, electrical potential energy due to dipole. So dipole is a system of charges, right? Dipole consists of more than one charges, which means two charges will be there. So two charges are equal and opposite charges separated by a short distance. So in that cases, dipole will have a certain potential energy. So we will consider an example. So a dipole is placed in an uniform electric field. This is the case. So electrical potential energy due to a dipole, in the sense the dipole is placed in an uniform electric field, minus q charge and plus q charge, separated by a distance of 2l. So we know the dipole moment is acting from minus p to p, and the angle is measured like this, and which is of angle of theta. So next, so whenever the dipole is placed in uniform electric field, it will experiences called torque. Correct. So torque is equal to P cross E. So we already learnt torque is equal to P cross E, which is also called PE sin theta. So depends upon the value of theta. Theta equal to 0 degree means torque will be equal to 0. When theta equal to 180 means torque is equal to 0. Theta equal to 90 means torque is equal to PE. So the value of torque is keep on changing with respect to the changes in theta. If something is changing with respect to theta, with respect to distance, with respect to time, we will use a mathematical operations called integrations. Many times I told, if some changes will be there, we can use some operations called mathematical operations called integration. Here our problem is we need to find out the electrical potential energy. Okay, so remember one thing, electrical potential energy is equal to negative of electrical force, and which is equal to work done by an external agent. So work done by an external agent is equal to electrical potential energy, and this is equal to work done by an electrical force. Remember this stuff. So always external agent work is equal to negative. So if you once you get positive, once you get potential energy, the negative of potential energy is called electrical force, and its same value is called external agent. So here we are going to find out the potential energy. Okay, before we are going to find out the potential energy means generally we will calculate called work, or we'll also call it as potential energy. So here we are going to find out the electrical force. So first, electrical force, work done by an electrical force. Why I am saying like this one, here electrical field will be there QE. So there is a force will be there, F is equal to QE and F is equal to QE in this direction. Both will act simultaneously, and there is a motion, that is called torque. So torque is experienced by, or torque is given by electrical force. So we are going to find out electrical force from theta 1 to theta 2, and F dot S in work power energy you are learning F dot S in first year. Here instead of F, force will come F dot d theta. Theta is the angle. So we are using integration. As I told, the torque is changing with respect to distance. So we will expand this stuffs. And what is expansion of this one? Integral theta 1 to theta 2 tau d theta. So tau into d theta into cos theta. Cos is the angle between tau and d theta. Tau is called what? Tau is called the torque. So if you look into this diagram, the torque, so there are two forces will be there, QE in this direction minus QE in this direction. So the dipole will rotate like this. So the dipole will rotate like this one, like this. So this is the direction of torque. Torque direction is clockwise, but the angle you are measuring in this direction. You are starting from here and you are measuring the angle like this. So torque is clockwise, Angle measurement is in anti-clockwise. So here torque direction clockwise, torque in clockwise, and d theta angle measurement in what directions? It is in anti-clockwise. Anti-clockwise. So what is the angle between them? One is clockwise, another one is anti-clockwise, opposite direction. So the angle between them is how much? Theta 1 to theta 2. Tau into d theta into here cos theta, it is cos 180. Cos 180 means you know the value of cos 180, which is equal to minus 1. So minus theta 1 to theta 2, minus will come outside, and which is equal to tau into d theta. This is the steps we have so far. So we are, why I am saying like theta 1 to theta 2 means initially we are assuming dipole is at a degree of theta 1. From theta 1 to the next angle is theta 2. So theta 1 to theta 2 I am moving. What is the energy I have? What is the energy spent by the electrical force? That's what we are going to calculate, will be here. Okay, so minus will be here, theta 1 to theta 2. Torque, instead of tau we will substitute the equations for this one, Pe sin theta d theta. So Pe is constant, take it out of the integrations, theta 1 to theta 2, minus will be here. What is the integral of sin theta? Integral of sin theta is cos theta or minus cos theta? It is minus cos theta. So the angle is from theta 1 to theta 2. This minus and minus become plus. So we will get Pe into, we are applying the upper limit minus lower limit, cos theta 2 minus of cos of theta 1. So this is the electrical force. This is not the electrical force, this is the work done by the electrical force. So work done by the electrical force Pe into cos theta 2 minus cos theta 1. So this is what we calculated now. But what is our aim? Our heading is electrical potential energy. Electrical potential energy, U is the negative of work done. So what is the formula for U is coming? We are multiplying with a negative. So minus Pe into cos theta 2 minus cos theta 1. So remember this. You can multiply minus inside so that you can write cos theta 1 minus cos theta 2. This is important. So potential energy is equal to minus Pe into cos theta 2 minus cos theta 1. Theta 1 is initially at what angle the dipole is located. That angle is called theta 1. From there, what angle I have rotated to the final positions, and that is called theta 2. Theta 2. So theta 1 to theta 2 we are rotating. We find the potential energy, we find the electrical energy, and this is electrical force. So this is called U, and this and if you want to calculate the work done by an external agent, that is also equal to same as U, right? Work done by an external agent is equal to U. So what it should come? The same formula, minus Pe into cos theta 2 minus of cos theta 1. So that will also hold the same formula for our use cases. So remember these two formulas are important. So in order to solve these cases. Okay. So next we are going to see, so this formula is important. We will use it in many places will be there, and we will see some special cases for this one. Okay. So I am keeping this formula. I am clearing this board from here. Okay. So I need some formula, for some assumptions. So initially I am assuming assumption, just an assumption only, theta 1 equal to 90 degree, which means the dipole moment is like this, minus q to plus q is like this, electric field is like this. So theta 1 is equal to 90 degree. So from 90 degree, if I am substituting, will be here, what should I will get? So initially it is theta 1 90 degree, then it is rotating to an angle of theta degree. So if you are substituting that cases, UE equal to minus Pe into cos of 90, not cos of 90, cos theta 2. Theta 2 is theta 2 itself. Theta 1 is cos theta 1 is 90. So what will happen? Cos 90 is 0. So we'll get minus Pe cos theta. So I can say generally the equations for a potential energy is equal to minus Pe cos theta. When? So theta means here I am assuming theta 2 is equal to some angle called theta. Okay, if that is the case, when theta 1 is equal to 90 degree, because first I am assuming initially the dipole moment, here you can see minus q2 plus q, this p is called dipole moment. If dipole moment is like this, then this is making 90 degree. From there, if it is rotating some angle, so that angle is given by theta 2, or that is also equal to theta, then the potential energy is equal to minus pe into cos theta. So initially from a certain angle, initial assumptions, initial angle, how much it is rotated, and that angle we are calculating, and we are saying potential energy is equal to minus Pe cos theta with an assumption of which is equal to cos 90 is the initial one. So this is the final position, this is the final position, and the initial position is at this angle. Okay, so in short I can say the potential energy formula. Okay, so the same potential energy formula I can write it as in another way, right? Generally, if I say potential energy is equal to minus Pe cos theta, so if it is given you two angle, I am rotating from theta 1 90 degree to, I am value theta 2 is equal to, theta 2 is equal to, theta 1 is 90 degree to, I am rotating an angle of theta equal to theta. If that is the case, then I can say final potential energy minus initial potential energy. What is the final potential energy? Minus Pe cos theta 2, cos theta, minus, what is the initial potential energy? Theta 1. So minus, tell me, so difference, so already minus Pe into cos of 90, this terms will goes to 0, you will get the same formula. So minus Pe cos theta is the general expression for finding the electrical potential energy. Okay, if theta 1 and theta 2 values will be given to you, so if you see this equation, minus Pe cos theta 2 final position, and if you multiply it will be here, this is plus Pe cos theta 1. Okay, so always if you multiply, minus will be here, means Pe cos theta 1 minus Pe cos theta 2, this minus and minus become plus, here minus and minus become plus. Okay, so this formula is exactly same as this formula, right? Cos theta 2 is a second term, cos theta 1 is a first term, from first where it is rotating, theta 1 90 degree it is rotating, so this minus and this minus become plus, here also you can see two minus will be there. So actually this formula is same as this formula. In short, I can say you can define potential energy in two ways. Potential energy at a point is equal to minus Pe cos theta. Theta is the angle between dipole moment P, dipole moment P, and the electric field. That angle is called theta. Okay, that angle is called theta. So you will get potential energy on that particular angle, and you want to find out the potential energy difference. So you see first where the dipole is located with respect to electric field, you will find the potential energy using the formula minus Pe cos theta. Then you will see where it is rotating, it is rotated maybe a 60 degree, not from there, not from the initial position. We will see some example. Then what is the potential? Again minus Pe into cos of 60 degree, you can get the difference between these two. Okay, this is the concept behind these cases. We will see some special cases. Okay, so remember this formula, this is most important for us in order to solve the questions. Electrical potential energy due to a dipole minus Pe cos theta. Remember this. Okay, fine. Okay, so we will take some couple of examples. Okay. Okay, so let me take three cases. Okay, when theta equal to 90 degree, first case, when theta is equal to 90 degree, torque is equal to what? Pe sin theta. So Pe into sine of 90 degree, which is equal to Pe, which is called, I can say, torque is maximum. And electrical potential energy is minus Pe cos of 90 degree, correct, cos 90, which is equal to 0. So electrical potential energy is minimum. When a dipole is placed in uniform electric field, it will experiences only torque. It will experiences only torque and no force. So total force will be equal to 0. Next one, when theta will be equal to 0 degree. When theta will be equal to 0 degree means your case will be like this one. Okay, here your case will be like this. Electric field like this, and dipole is located minus q to plus q, separated by a distance of 12. So this is dipole moment, electric field 90 degree. Now here minus q to plus q, separated by a distance of 12, electric field like this, dipole is like this. So E and P in the same directions. We will find a torque. Torque is equal to PE of sine of 0, which is equal to 0. No torque exists. And we'll find potential energy is equal to minus PE into cos of 0, which is equal to minus PE. So this is torque in the minimum value. Torque will have a minimum value, and this is potential energy will have a minimum value. I have given you this example. Whenever if you have placed the dipole moment P is parallel to electric field, that condition is called a stable equilibrium. Hope you remember, we have already written in the notes called stable equilibrium. What is called stable equilibrium? Stable equilibrium means if you have given any disturbance to the system, it will come back to the original position. For example, listen once again carefully. Minus q to plus q will be here. Now, if you simply rotate it like this one, let me take another color. Okay, suppose if you simply rotate it like this, so minus q and plus q. So you simply rotated certain angle theta. So what will happen? There is an electrical force will be here. Whenever this blue line will becomes like this one, electrical force QE will act like this, and minus QE will act like this one. Because these two forces will pull, and it will restored back to this position, initial position. That is called stable equilibrium. I will repeat again. Initially minus q to plus q will be here. Dipole moment is in this direction, P. Electric field in the direction. Both are parallel. Angle between them is 0 degree. Now, if you give a small disturbance to the system, is like this. So what will happen? If you give a small disturbance means it will rotate like this one. So there are forces will happen. Whenever it is rotated, theta is not 0 degree, theta is some other value. So what will happen? A QE force will pull like this, a minus QE. So both forces will make it back and keep it back. So which means it will come back to the original position itself. And that condition is called, and this condition at this stage, this condition is called stable equilibrium. This is a condition of stable equilibrium. So remember this point, what is called stable equilibrium. When theta equal to 0 degree, at stable equilibrium, potential energy is minimum. Okay, then we will see another cases when theta is 90, theta is equal to 0, and the other cases like theta will be equal to 180 degree. Theta equal to 180 degree means your electric field vector is like this, and dipole moment is opposite, minus q to plus q, opposite direction. This is called P. So electric field in one direction and dipole moment in another direction. If such cases are exist, what will happens? Okay, both are opposite direction, right? So torque is equal to what? PE into sine of 180, which is equal to 0, and the torque will be equal to PE into cos minus PE into cos 180. So what is called PE? So this is not torque, this is called potential energy U, and potential energy, I can say the potential energy at this stage will have a maximum value. Here it should have a minimum value. Okay, here also it is minimum, but I don't want to write it minimum because comparable to this is minus P, this is positive P, this is just 0. So which one is a less value? 0 will be there, a minus value will be there, a positive value will be there. Which one is lesser? This is the minimum value. Most minimum is this one. So we can put it as this for minimum, this you can remove minimum, and this is the maximum value. So maximum value means under these conditions, if you are giving some disturbance to the system. Now if I am giving some disturbance, I will move like this one. So minus q and plus q. So what will happen? If you are moving minus q, if you are giving small disturbance, some small angle called theta, if you are giving some disturbance to the system, what will happen? Because this minus q will pull in this direction and the plus qe force will be here and qe force will be here. So once this is keep it like this one force like this, another force like this will move in opposite direction, which means it will not come back to the initial position. This will not come back to the initial position. If it is not come back to your initial position, then this is called what? It is not restoring. It is not restoring to the original position. Then this is an example of an unstable equilibrium. This is I already told when I am taking about the talk, but I again repeated. This is also this is called unstable equilibrium. Remember this one. This is entrance point of view. This is important. So we know what is called stable equilibrium at theta equal to 0 degree. When theta equal to 180 degree, this is called an unstable equilibrium. In stable equilibrium, if you give any small disturbance, this dipole will come back to the original position. It will retain because of this QE and QE. If you are moving like this will pull it back. But here, if you slightly move it back, nobody will be there to keep it back in the position. It will go in the same direction because of this force. Here you see the forces in this direction, so it is pulling back. Here if you give a disturbance, the forces is not in this direction, forces is back, so nobody is available to keep it back. Then it is called unstable equilibrium and this is called stable equilibrium. So remember all these three concepts. This is important to remember all these things. Okay, so potential energy, the minimum value of potential energy is minus P. Such condition is called stable equilibrium. I will give you a practical examples. Okay, so let me clear the board at this level in order to explain more about the stable and unstable equilibrium. Suppose if you remember, I have a ball like this one. Okay, so I placed one small ball will be here. I placed the same ball will be here. Two position I have placed. Where the ball is more stable. Here the ball is more stable, right? More stable means with respect to the potential energy. In case of normal situation, when height increases, potential energy increases, right? mgh, normal potential energy. So this is more unstable, correct? Because it is just sitting there, and if you give a small tick, what will happen? It will fall down. But if you give a small tick, what will happen? It will just oscillate and come back to the initial positions. So which will just rotate and it will come back to the original. So this is much more stable, which means it can come back to the original position. But if the ball is on the top and if you give a small tick, what will happen? It will just fall down. It will never come back to the initial positions. So this is an unstable. So with respect to the ground, this will have U max, high potential energy, but this will have minimum potential energy. Correct? If you have taking from a ground level, for example, this I am assuming it's a ground, this will be placed on a stand. Then this height is 5 meter and this height is 10 meter. So more potential energy but unstable. Less potential energy, more stable. This is a very fundamental principle in physics. So whenever you have a less potential energy, you are more stable. When you are having a higher potential energy, you are more unstable. Okay, there is a high chance to fall down. Whenever you are heighting, you are going away from a ground level, there is a high chance you will become unstable and there is a high chance you may fall down, and you should have a high risk also. But whenever you are in a small height, you will be very safe and you will have a minimum potential energy, and because of that one you are in a stable equilibrium position. This is a very funda of physics. Okay, fundamental system of in physics. Okay, fine. Okay, we'll see some small questions connected to this one, some examples questions to make the theory become much stronger, we will say. Okay, so my first questions to you, my first examples to you. Example number 1. Okay, so initially the electrical energy or the electric field is like this, and the dipole is placed like this, plus q to minus q, p is like this. Okay, so question is, what is the potential energy? What is the potential energy needed to rotate to rotate the dipole to 180 degree. What is the potential energy is required to rotate the dipole to 180 degree? So we know the initial potential energy is equal to minus PE cos theta. Theta is what will be here, 0 degree. So it is called minus PE. Final potential energy means I am rotating to 180 degree. 180 degree means what is the final structures now we have? Final structures is minus Q and plus Q and P and E, which is opposite directions. So if you are rotating like this one, the final potential energy is minus PE into cos of 180, which is equal to PE, and the potential energy required, the potential energy needed. So potential energy needed potential energy, required potential energy, final potential energy minus initial potential energy. Final is PE minus initial is minus PE. So total potential energy required is equal to 2 times of PE. This is just an example I have given to you with the help of the concepts what we have learned today. Okay, fine. Next one. So hope this is clear to you. Fine. And we'll take another example. Example number 2. Okay, so initially the dipole is, the electric field is like this. This is an uniform electric field and the dipole will be minus Q to plus Q and will have a 60 degree. Now the dipole is in this position, so plus Q and minus Q, and this angle is 60 degree. Okay, what is, and this is called the initial position. Initial position. And this is called the final position. Final position. Okay, now the questions to you is, what is the work done? What is the work done by electrical force? Work done by electrical force to move the dipole, from initial positions to final position, which means dipole is at one angle, initial position to final position. Here you have to remember the question. The question is not asking about the potential energy. Question is asking about the electrical work, the work done by the electrical force. Work done by the electrical force is equal to negative potential energy. So we know the formula, U is equal to minus of work done by electrical force. Work done by electrical force. This is also equal to, I can written as work done by electrical force. Work done by electrical force equal to negative of potential energy. Both are correct, right? This minus signs can be taken to left side. So I'm going to find out U, then I will substitute for this one. So initially the initial potential energy like this. So we just make an angle of theta. So minus PE into cos of 60 degree. So what is cos 60? Cos 60 means 1 by 2. So minus PE into 1 by 2, which is equal to minus PE. What is the final potential energy? Minus PE into cos. Very careful. 60 degree, 60 degree. Here also the final potential energy is not 60. Angle is always calculated in this direction. So what is this angle? This is the final. Total angle is 120 degree, not 60. The 60 is given to confuse you. Always you have to take an angle like this one. So this is the final angle is cos of 120 degree. So minus PE into, what is cos 120? Minus 1 by 2. So PE by 2. This is also by 2. Okay, so PE by 2. So how to find out the potential energy? U equal to U final minus. We calculated about the final potential and we take the difference of final potential minus initial potential. So PE by 2 minus PE by 2, we got PE. Next, our question is, what is the work done by electrical force? Work done by an electrical force will be equal to negative of potential energy. Potential energy we have calculated PE. So work done by an electrical force, which is equal to minus PE. So our answer to the question is work done by an electrical force equal to minus P. Answer is minus P. So always you have to remember, we are taking this angle. This is 180 degree. sorry, 120 degree. Initial angle is 60 degree, and this 60 degree is given to you just to confuse you. So you want to take the angle always in this direction. This is anti-clockwise direction. Okay, so you have to take total angle. So here it is 60 and here it is 120. So you have to substitute 120 and you will get the answer for this questions like this. We'll move to the next example. So two examples are clear, right? Wherever you write one step in physics, that should have some justifications. You cannot take some sign plus or minus, something like that. Okay, so example number 3. Okay, in example number 3, you have an electric field like this. Okay, so the dipole is placed like this, dipole moment like this, initially an angle of how much degree you can say? 60 degree. So it is 60 degree. Okay, so the question is like, whenever it is placed into, question is like this, whenever what is the work done by an external agent? Two things will be there. So we need to we know if you do some external work or if you do some electrical force work by the electric field, then the dipole will come back to the final positions of theta equal to 0 degree. So the question is like, when the dipole moment is parallel to, when the dipole moment is parallel to the electric field, when the dipole moment is parallel to the electric field, when the dipole moment is parallel to the electric field, the angular velocity, when the dipole moment is parallel to the electric field, the angular velocity at the stable equilibrium position is, at the stable equilibrium position is what? At the stable equilibrium position is dash. So we have a system and the system is given, the angles are minus q to plus q, which are separated, which are at an angle of 60 degree. When I am keeping this body into this position, which means in a stable, because the minus q to plus q and the dipole moment is keeping parallel to the electric field. When the dipole moment is parallel to the electric field, the angular velocity at this stable equilibrium position is. Okay, so whenever this dipole is come to this equilibrium states, equilibrium state means stable equilibrium states, then what will happens? Then during the times, now you remember, now it is minus q to plus q, the dipole is like this. I am trying to keep it at stable equilibrium. Now once it is at stable equilibrium, once it is come to stable equilibrium, which will be just jerking like this, correct? It will be just jerking like this. So just jerking like this means this dipole is not ready to go out of that state because it's in stable equilibrium. Stable equilibrium means it is always would like to stay in this like this. So whenever if you give a small disturbance like this one, it will always come back to and it will be settled. So initially it will just jerk like this one and it will come back to the parallel to the electric field. So whenever if you just keep it, then this will have a certain oscillations. So you need to find out that oscillation frequency. That oscillation frequency means that oscillation speed, angular speed, because it is rotating like this, not a linear motion. Linear motion means you will find velocity. If the motion is like this one, you will find angular velocity. So you want to find out what is the value of angular velocity at this position. Okay, so we are going to find out angular position. So initially one position and finally one position. So I am assuming initial, here we have to use a concept called a conservation of energy, all this kind of question. So final kinetic energy is equal to final potential energy plus and final kinetic energy. Initial kinetic energy, what is, tell me, minus PE into cos of 60 degree. I am assuming initially it is at rest, then I am moving down. So initial there is no speed, there is no rotation, it is initially it is like this. Then I am keeping it and taking to the stable equilibrium position, then it will have a jerk and it will be rest. So what is that jerking speed? So final potential energy. Final potential energy means, tell me, minus P into what is the final angle will be there? 0 degree. So cos of 0 plus final kinetic energy. Kinetic energy is not half mv square here. Why? Half mv square is not here. Half mv square is for a linear motion, velocity equation. This is a rotational motion. So you want to know what is a rotational motion equation. Rotational motion kinetic energy equation is half I omega square. If you don't know, write it on the note side. On the notebook right side. Kinetic energy of rotational motion is equal to half I omega square. Okay. So we'll simplify this one. Before that, we need to get the value of IA. I means moment of inertia. So if you see, this is one charge which will have one mass. This is another charge which will have same mass. So the moment of inertia we are calculating with respect to the axis of rotation, which means you can assume minus q and plus q, two charge, mass m, distance between them 2l. So to the center, with respect to the point only, this is rotating. So this will be like this, and this can be rotated like this. So the center will be remain same. So up to the center, L distance away, this is also L distance away. So both are L distance away meters. So the moment of inertia is equal to mr square is a general formula. Mr square is a general formula. But here two things will be there. Ml square plus ml square, two charges. So total moment of inertia is 2ml square. M is for one charge. So minus PE cos 60 means minus PE by 2 is equal to minus PE plus 1 by 2 into 2ml square into omega square. 2 and 2 will get cancelled. Minus PE is taken to left hand side. So what it will become? It will become PE by 2. PE by 2 is equal to, what is coming on the right hand side? ml square omega square. ml square omega square. We need to find out omega. So we know P is equal to 2q into L into electric field divided by 2 is equal to ml square omega square. L cancel, 2 get cancels. So balance I am writing here. So what we will get? Q will be there and E will be there, which is equal to ml omega square. Balance we are writing. We are going to find out angular velocity. Our question is angular velocity, which means omega is equal to root of QE divided by ml. This is the answer for the question. Root of QE divided by ml. So question is asking about the angular speed. That's what we are going with the concept of energy conservation. Initial potential energy plus initial kinetic energy is equal to final potential energy plus final kinetic energy. So we are applied the formula minus PE cos 60 plus 0 is equal to minus PE cos 0 plus half I omega square. Why half I omega square is coming here? Because it is a rotational motion. It is a rotational motion. Okay. It's purely a rotational motion. It is not a linear motion. If it is a linear motion, half omega square will come. So whenever you see some questions in physics which has n connections with initial and some potential energy and some kinetic energy, definitely if you see like this a question, definitely you know a dipole is placed in uniform electric field, it will experiences a torque, it will have some potential energy. So definitely some potential energy will be there, and the question is asking about angular velocity. Velocity is related with the kinetic energy. So somehow you need to connect potential energies with kinetic energy. So there is only one chance will be here. Initial kinetic energy plus initial potential energy is equal to final kinetic energy plus final potential energy. That is the relations I have used. If you see such kind of questions wherever you can able to connect kinetic energy with the potential energy relationship, you have to use this concept always. Remember, this is very important throughout the journey in physics. Hope you understood. Two topics majorly we have seen so far, and one is electrical potential energy, the general equation. Second one, what is the electrical potential energy in case of a dipole? Simply minus PE cos theta, and work done by an external agent is equal to the potential energy, but work done by an electrical force is equal to minus of potential energy. Okay, hope you got the concepts very clearly. Everything should be there in your note, and hope you understood these topics. we have to move to the next topic also. Okay. Hi dear students, welcome to the next topic, and we are going to start the another important session from electrical potential and capacitance, which is actually electrical potentials we have completed. We are moving to the next major topic, which is called capacitance. So write down the heading called capacitance. What is called capacitance? Capacitance is actually, it is a device. Normally this device, which we can see it on your ceiling fan, normally it is there in most of your fan. We can see it's very commonly. Okay, if you look into the ceiling fan, there you can see a white box, or it is something like a dappa. Okay, so it is just like a cylindrical structure. So that you can see, and that is called capacitance. Okay, so capacitance is nothing but it is a device. So we'll write, so capacitance is a device used to store charge. So if I want to store some charge, the capacitance is a device which we are used to store the charge. Unit of capacitance. So unit of capacitance. Capacitor is a device. That property is called capacitance. So the unit of capacitance is called farad. Practical units will be there. Farad means it's a very high value. So practical units of capacitance. Practical unit is microfarad. This normally we are representing using a letter called F, and practical unit is called microfarad. Now we need to derive an equations for a capacitance. So what is capacitance? So capacitance is similar to our resistance. Okay, the equation is more or less similar. So capacitance of a conductor C is equal to charge divided by voltage. This equation is very important. Capacitance of a conductor C is equal to Q divided by V. So this is similar to our resistance equations, right? Resistance equations we have learned. R will be is equal to V by I. This is similar to this one. Why I am saying similar means, whenever for a conductor, if you increase voltage, current will also increases. So same way for a conductor, if you are increasing charge, then voltage will also proportionally increases, because voltage is equal to KQ by R. Okay, so if you increase the numerator, denominator is also increases. So the capacitance is, using these equations, we cannot say capacitance is depends upon charge, capacitance is depends upon voltage. No, capacitance is independent of charge and voltage. But what is capacitance is depends. Capacitance is depends upon the dimension. For example, resistance, you have learned an equation called R is equal to rho L by A. There is an equation for resistance. R is equal to rho L by A. L is the length of the conductor, A is the area of cross section. These are the physical properties of the conductor. So same way here, the physical properties means the physical nature, like length, like the length and area of cross section. So similarly here also we have certain physical quantities like area of the conductor, length of the conductor, separation. So many factors, I mean physical natures are depends upon capacitance. So my next point is capacitance is independent of Q and V. So which means it is not depends upon charge, it is not depends upon voltage, but it is depends upon the dimensional quantities such as length, area of cross section, etc. Okay, so hope you understood this concept. This is important. So it's a device used to store the charge, and its unit and what is called capacitance. The formula, capacitance is equal to Q by V for a particular conductor. If you have, for example, if you have taken like a 3 conductor A, conductor B, conductor C. So for conductor A, the capacitance value is fixed because its dimension is fixed. So if you have another conductor, a big conductor, its name is B, then the capacitance of that conductor is fixed. It can alter, the capacitance of that conductor can alter by changing its length, its area, etc. So such physical parameters, such dimensions, if you have changing, then this will be getting changed. That is the whole concept behind this part. Okay, so we'll move to the next part. Next part means capacitance of a spherical capacitor. Okay, so listen very carefully, this is also important. Okay, capacitance of a spherical capacitor. So write down the heading, capacitance of a capacitance of a spherical capacitor, capacitance of a spherical conductor, capacitance of a spherical conductor, and a spherical capacitance. So listen to the board very carefully. I have a conductor, a spherical structure whose radius is r, which will have some charges on the surface, and its charge will be equal to q. Then I want to find out what is the capacitance given by the conductor. So always, in order to get capacitance, there are two layers are required. One positive layer will be here and one ground level. So ground means we can consider this is one positive, so the another outer layer, so two layer is required always to have a capacitor, because capacitor is a device which consists of positive plates and negative plates. Two plates are required. So here positive plates will be there. Then you can ask me a question, where is the negative plates? Negative plate is at infinity. So at infinity the negative plates will be here, which means it is at ground, or you can say it's a zero potential area. So how we are calculating the capacitance value for a spherical capacitor? So this is a capacitance, right? So to find out the capacitance, we know the formula is equal to C is equal to Q divided by V. V is the potential created by the conductor. So C is equal to Q divided by. What is the formula of voltage at the surface of a conductor? It is KQ by R. Already we have learned this formula under potential. So Q and Q get cancelled. So it become R by K. What is K? K is 1 by 4 pi epsilon 0. So once you simplify, we'll get 4 pi epsilon 0 times of R. This is the value of this spherical capacitor. So the value of spherical capacitor C is equal to 4 pi epsilon 0 R. This is a direct formula, direct equation. C is equal to Q by V we have learned. We know what is the value of V, and we are substituting the value of V, and we are solving these factors. So this is what actually we are doing in these steps. So in order to form a capacitance, we need actually a positive layer and we need actually a negative. So this is like a negative circle, and here it is a positive circle. So between these two the capacitance exists, and capacitance, if you see, will be equal to 4 is constant, pi is constant, epsilon 0 is constant. So it is depends upon what called R. R is the dimension of the circle. So R is the dimension of the circle. So this is depends upon the dimension of the device. It's not depends upon any other physical quantities. Okay, good. Okay, so second topic is over, and we will move to the next topic. Next topic means energy of a spherical capacitor. So now we know capacitor. So capacitor is a device which is used to store the charge. Charge means energy, battery. So energy of a spherical capacitor. Energy of a spherical capacitor. Okay. What is called energy? Energy means a battery. Suppose if you are going to a shop and if you are buying some battery, normally 1.5 volt, we can put it in our any of our toys, so that it will work unless until its battery is drained out. So energy, so you are using some energy, and that energy is called electrical energy. So here also the energy of a spherical capacitor, because capacitor is storing the charges. So listen, initially I have a spherical structure, a conductor. Conductor has no charge. So at T will be equal to 0. There is no charge on the conductor. So Q is equal to 0. And the voltage. So voltage will be equal to 0. Or I can say capacitance. Capacitor. There is no charge means capacitance is equal to 0. So at a time t is equal to t, means after certain time I am giving some charge, q is equal to q, that time capacitance is equal to q by its voltage. Now after a long time, I am giving the charge, I am supplying the charge, I am supplying the charge. So charge will be increases. So after a time t is equal to infinity, the charge rises to capital Q. Its full capacity. Its full capacity is capital Q. Now after time t is equal to infinity, this will have full charge, capital Q. And during this time, its capacitance is equal to Q by V. Okay. Now what we need to calculate? Energy. Energy means what? Energy is the work done. Okay, in case of capacitor or in case of potential, it is we have an infinite point will be here, infinity. So voltage at infinity, here this is a voltage. So we are calculating the energy. So energy of a capacitor means the work done by an external agent to bring a charge. We can say a dq amount of charge, a small amount of charge is bringing work done. So it's a small charge means small work done. So W external work done, external agency. I am doing a work to bring a charge from infinity to a particular point, and whose circle or its radius is equal to R. So we know dW external is equal to work will be equal to what we call it as integral. Why? I'll tell you. Into V into dq. We have already learned this equation. W is equal to VQ. This is the relations which is connecting between voltage and potential. Here the voltage and the charge you are bringing from one point to the another point, which means you are bringing from infinity to this point. So work done which is equal to V dq. Mostly you have remember different set of equation. dW is equal to integral into tau into d theta. This is one equation. Work done will be equal to integral F into ds. These all the work equations. Work equation in rotational motion first year. Work equation from work power energy first year. Work equations in electrostatics second year. So 3 work equations. Okay. So we'll substitute. What is V? V is equal to Q by C. Okay, so V is equal to Q by C. Here I am writing Q by C because I am doing this job for a period from t is equal to 0 to infinity. So during the time, the value of Q changes from how much? From 0 to Q. Okay, I am starting my work at t is equal to 0, and the capacity, this spherical conductor is getting fully charged at a time t is equal to infinity. After a long time, this is charged to a full charge. Its full charge is capital Q is bigger, small q is lesser. So small q is an intermediate stage. So from the intermediate stage, initially it is 0, finally it is capital Q. So the intermediate stage is Q, and this Q is changing, and finally it is reaches to Q. So Q by C into dq. Why I am writing Q? Why I am not writing capital Q? Mean capital Q is a final stage, small q is the initial stage. I want the changing stage. Whenever there is a continuous change with respect to time, with respect to distance, with respect to angle, with respect to any other factor, then we will use integration. What is changing? The q is changing will be there. Once you reach us at capital Q will not change. Once you reach us at 0, from 0 the next level, next to one increment is called small q. Then this small q accumulated, and finally we got capital Q is the final value. So again integration limit 0 to q. So what is constant will be here? 1 by c is constant. Integral 0 to q and q into dq. Okay, q into dq. What is the integrations value? Will be here 1 by c into q square by 2. We will apply the limit from 0 to capital Q. Once we apply the limit, what will get? 1 by c into q square. 1 by c into q square by 2, which means I can say q square by 2c is the energy of the capacitor. So I can say energy of the capacitor E. Some textbook it is also referring U. I am using U will be here. So I can use U from NCERT textbook, and U equal to Q square divided by 2C. This is the energy of any capacitor. I can say this is the energy of any type of capacitor which has 2-layer structure. So this is a capacitor Why this is a capacitor means here you want positive plates, so then where is the negative plates? Negative plates will be there at infinity. So this is the energy of a capacitor. This is I have derived for a spherical capacitor, any structure, any shape, this is the energy. Because here we have not played any generic things. We have not we have not done any specific things. Specific thing means the specific parameters which is related with the resistance related with the radius or any spherical related parameters such as area and the perimeter like 2 pi r square. No such things are not involved in the equation. So this is a generic equation to find a capacitor is there. What is the energy stored in the capacitor? You will say q square by 2c. Any type of capacitor, it is q square by 2c. Okay. So I am taking this area. You can note down these points. Then we'll move further into this part. Okay. So q square by 2c. I know C is equal to Q by V. So I can say Q is equal to CV. I am substituting these equations will be here. So U equal to what is Q square? C square V square divided by 2C. So C and C will get cancelled. So we will get half CV square. This is another equation of energy. Next, U equal to Q square by 2C. C I am substituting. What is called as C? C is equal to Q by C. Okay, Q square divided by 2C. C is equal to Q by V. We are substituting. So Q by V. Q and Q will get cancelled. So we will get QV. This is another equation of energy. So there are three equations for energy. We are summarizing them. U equal to half CV square, which is equal to Q square by 2C and which is equal to QV. These all three are the equations of energy. Very important. Very important. You will come across this one with the different questions. Okay. So fine. So I am clearing the board. I want to give one important point to you. Here I have written work done by an external agent. Work done by an external agent. Work done by an external agent means externally it is doing some work. We have already learned potential energy difference. Final potential energy minus initial potential energy is equal to negative of work done by which force? Electrical force. Correct. Last sessions we have learned. Last topic. Work done by electrical force equal to work done by an external agent. So work done by an external agent and which is equal to half CV square, which is equal to Q square by 2C and which is equal to QV. Remember these stuffs also. This is also important to remember. Okay, electrical force and external. External work done is positive. Whenever if somebody is asking electrical force, then minus half CV square minus Q square by 2 minus QV will come. Okay, hope you understand this concept behind this factor. Okay, so that is clear. So just I want to make sure that you have to always read the questions carefully. A question may ask the work done by an external agent, or questions may ask the work done by an electrical force. So based upon the questions you have to give a correct answer. We are going for an important topic. Next one is called a parallel plate capacitor. So write down the heading called parallel plate capacitor. Parallel plate capacitor. Okay, parallel plate capacitor means this is also similar to a spherical capacitor, but the only difference is like here we have two plates are available. One plate is positive plates and another plate is a negative plates. The distance between the plates is equal to small letter d. Okay, I want to derive an equations for capacitance. So capacitance C is equal to Q by V. Then a charge plus Q, then a charge minus Q. Area of the plates, this is A area of cross section, area. Okay, it's a rectangle plates. So C is equal to Q by V we have to find. Okay, Q is the any one of the charge. Both charges must be equal. So we want to find out potential. We have not learned anything in case of spherical capacitor. We know what is the formula for potential of a spherical conductor, kq by r, but here we don't know what is the formula of a plate with a positive charge and negative value, and what is the value of potentials we don't know. So we need to find that value. To find that value between the two plates, so always we are interested the things happening between positive and negative. So this is the point will be here. Because of the positive plates, electric fields are going away. Because of negative plates, electric fields are coming into that. So two electric fields will be here, E1 and E2. So we know total electric field is equal to E1 plus E2 in between the plates. So which means sigma divided by 2 epsilon 0. This we have learned when starting off electric charges and electric field. Okay, electric field is due to a plate of capacitor. If you have not remember, please go back to your notebook and see that. So sigma divided by 2 epsilon 0. So if you add two electric fields vectors are same direction, so we can add. So this will give rise to 2 sigma by 2 epsilon 0, which is equal to sigma divided by epsilon 0. Okay, what is called a sigma? Charge divided by area. So QA epsilon 0. Next we want to find out voltage. Voltage is equal to what? Voltage is equal to electric field into, if you are finding electric field will be here, then into distance between the plates. V is equal to E into D. So what is V will come? Now Q D divided by epsilon times of A. We are going to find out the value of capacitance. Now we are substituting and we are fine. So C equal to Q by V, the value we are substituting, QD by epsilon A. So Q get cancels. We got C equal to epsilon A by D. This is the equations for the capacitance of a parallel plate capacitor. Okay, so this concept, this is the key point will be here. This we have not studied anything new. This we already studied in the previous lecture videos, electric charge and electric field. There we have described this concept. This is definitely there on your notebook, and if you are not remembering, kindly go to that sessions and revise it and come back to here so that you will remember this one. So this already we have taken class. So this is a new, so from there this is a just we are resubstituting the things in the equations, and we got epsilon A by D. Look at here. When I am starting this topic of capacitance, I told you capacitance depends upon the physical dimensions, not depends upon charge, not depends upon voltage. If you look into these equations, capacitance depends upon the area of cross section, which means area of the plates, and the distance between the plates. So epsilon A divided by D. So this is the equations for a parallel plate capacitor. Okay, fine. We are going to move to the next one. Small topics will be here, and that small topic is called, that is related to the parallel plate capacitor only, but force experienced by one parallel plate capacitor due to other plates, which means that what? So write on the heading, force experienced or exerted, experienced by one plate of a capacitor, because due to the other plate, due to the other plates. So we have a parallel plates. Okay, you know we have a parallel plates, one is positive and another parallel plate it is negative. So positive plates will be the positive plates will attract towards this one, and the negative plates will attract towards this one. This all separated by a small distance of d, and area of cross section wise both are same, so there is an attractive force will be there. Why there is an attractive force? Of course it is a different material in the sense that charges are different. Okay, one is positive and another one is negative. If you see will be here in case of a capacitance, here nothing is filled, so this is an air medium. So a capacitance can be made up with anything can be filled between the medium, anything in the sense any materials. That material is called dielectrics. We will learn more about this dielectric in detailed sessions in later. So here two plates will be there, positive plates and negative plates. In between the plates, the air is the medium. So the medium will be here, it is called air, and this air is called a dielectric. Dielectric means it is nothing but an insulator. It is dielectric medium. So dielectric is nothing but an insulator. So any insulating medium will be there, either it is air or it is paper or it is mica, anything. But in general, any dielectrics medium will be there. But our topic is, we need to find out what is the force experienced by one plate. So force will be equal to Q into E. Q into E. This is quite simple. So what is the electric field due to one plate? Sigma divided by 2 epsilon 0. Okay, so Q into, what is sigma? Charge by area. So A 2 epsilon 0. So we'll get Q square divided by 2 times of epsilon A. This is also important. This is the force experienced by a conductor. Okay, force experienced by a conductor. Force experienced by a conductor means a plate due to the presence of the next plate, and this is the equation of the force equations. Okay, next. Okay, so force equations will be there. So if we have so what is the work done in this cases? So we know work will be equal to force into distance. What is called work? Work will be equal to work done by an external agent. Work done by an external agent means this is one plate. This plate will experiences a force equal to Q square by 2 epsilon 0 on this plate. What force it will experience? It will experience an attractive force. It will try to pull. How much distances this plate can move towards these plates? D distance away. So with the help of if an external, so the work done by an external agent means these plates. So I can say simply, I can say maybe I can say work, or I can say work done by the plate. I can say like this. So this will be more clarity for you. So work done by the plate is equal to the force experienced by that plate into distance. Either this plate can move towards other plate, or that plate can move towards this plates also. So work is equal to, simply work is equal to Q square divided by 2 epsilon 0 A into D. D is the distance between the plates. Okay, so I can say this is the initial structure, and with the initial structure this is the force experienced. If I want to move one plate by a distance of D meter away, if I want to, two plates will be here. So the force experienced by one plate is given by Q square by 2 epsilon 0 into A, and force into distance is called work. And how to find out the work? If I want to move one plate towards another plates or away from that by with a distance of D meter away, then I have to do a work will be equal to Q square divided by 2 epsilon 0 A into D. So this is the formula for force and work done. So force formula, it is important. Okay, hope you got the point. Force and work and capacitance. So we'll just summarize what are the things we have learned. We have learned about what is called a capacitor and certain properties of the capacitance. Then we have learned about the spherical capacitor. Then we have learned about the energy of the capacitor. Then we have learned about the parallel plate capacitor. Then we have learned about the force experienced by one plate over another plate. So this equation. So almost 4 topics will be there within capacitance we have learned. Still we have other topics will be there, and we will come up with the next sessions with next topics. Hope you got something new and you have learned something new also. So enjoy your study, and yeah, thank you.